Welcome back, homeostatic meat wagons. Today, we are going to talk about graphing polynomials. And I know what you're thinking, kids. You're thinking to yourselves, Mr. Barton, my three greatest fears in life are being honest with myself, disappointing my parents, swimming, counting to three, and graphing. I know. It's tough. Don't worry. I avoided greatest fear number 4, and your parents love you. Don't worry about it. Good chirping, kid. But we're gonna have to face our graphing fear today. We're gonna graph some polynomials. Lucky for you though, you're not actually gonna have to graph a whole lot. You're gonna more have to look at graphs and tell me what's pretty about them. So, what our objective is we're gonna try and determine some key features of the graph. Specifically, we're looking at polynomial functions because that's what we've been looking at for this entire unit. So some of them will already be graphed for us. Some of them we will use a graphing utility to graph. And then there's some equations that we're going to just take a little peek at the equation and figure out some important stuff from that. So let's do the easy stuff first. Let's talk about vocabulary. So we'll talk about this and we'll talk about vocabulary. So the end behavior of polynomials. All that means is that if you're looking at a graph of your polynomial, let's say it's red and let's make it skinny. Let's say our polynomial looks like this. All we're talking about for end behavior is what does that arrow do and what does that arrow do? What directions are they pointing? Are they going left? Are they going right? Are they going up? Are they going down? Stuff like that. So for polynomials specifically, there are some patterns that we should be aware of. That way we don't have to graph them and look at them every single time. We can just look at the equation, look at a couple of numbers, and go, okay, I already know the answer. I don't need to graph it. So it is the appearance of the graph on the left. We're going to say that's x equals negative infinity, or probably more like x goes to, we'll pull an arrow there, negative infinity, and the appearance of the graph on the right. So x goes to positive infinity. The end behavior can be determined by looking at the leading coefficient, and really we're just looking at the sign of the leading coefficient. The number doesn't matter at all. And the degree of the polynomial. The degree is something we'll see on the next slide. So the degree is the largest exponent of a polynomial. It's the biggest number, right? No cap. The leading coefficient is the number or the coefficient attached to the variable with the largest exponent. This says the number at the beginning of the polynomial, but it has to be in standard, I spell standard form for that to be true. If it's not in standard form, it could be in the middle or the end. So hopefully everything you ever have to deal with in your whole life is in standard form. Probably won't be, but you know, c'est la vie. All right. So let's talk about what the degrees mean, right? Let's look at the pattern here. So let's talk about an even degree first. Even degree means if we're looking at our polynomial, we have like 5x to the fourth minus 3x to the third plus 17x squared minus 16x plus 1. Okay. Even degree means that this largest exponent is an even number. Okay. That's all we mean by even degree. It could be 4, could be 2, could be 16, could be 201. No, that's an odd number. I panicked. 202. So even, it just means it ends in 0, 2, 4, 6, or 8. Okay. If it is a negative even degree, and this is a little misleading. When we say negative, we mean the leading coefficient, okay? The negative positive, we're referring to the leading coefficient. So if we have a negative leading coefficient with an even degreed function, both ends go to negative infinity. So what that means is that if this 5 were negative and we had an x to the fourth, our graph would look like this. Both ends are going to negative infinity, meaning they're pointing down. So if you want to write that a little more like teenagery, you could just write both ends go down. Okay. If we have a positive leading coefficient and our exponent is still even, then both ends go to positive infinity. So it would look more like this. So both ends are going to go up. Both ends go up. Okay. So the idea here is if the degree is even, the end behaviors are going to be the same. They're going to match. So either both down or both up. Guess what happens when the degree is odd? I bet you can't guess. I bet you can't guess right now before I go to the next slide. Nuh-uh. No way. You can't do it. So if it's an odd degree, then the end behaviors go in opposite directions. So all an odd degree means is that the exponent is either a 1, a 3, a 5, a 7, or 9, or any number that ends in those numbers. If we have a negative odd degree function, it goes from up to down. So what it would look like is this. So it would start with an up arrow and then it would turn into a down arrow, right? Sometimes you'll see these called like up, down functions. I don't know. There's a bunch of weird names that probably aren't like accepted in academia that teachers just tell students because they don't like explaining stuff. But yeah, so negative leading coefficient, odd degree, the left side goes up, the right side goes down. The leading coefficient just tells you what the right side does. Because it's negative, the right side goes to the negative infinity, and then because it's opposite, the other side does the opposite thing. Okay. If we have a positive odd degree function, it goes from down to up. So it would go like that. So it goes from a down arrow to an up arrow. Okay, cool. So let's determine the end behavior of a few of these. So the way we're going to write it is as x goes to negative infinity, f of x goes to something. And then as x goes to infinity, f of x goes to something else. I'm going to go ahead and cheat a little bit here. I'm going to copy this, and then I'm going to paste it a few times so that I don't have to write it, but you can. Okay. So what I'm going to do is I'm going to draw a little like sketch of what it'll look like, and we'll fill in the end behavior. So here we have a positive leading coefficient with an odd exponent. So we're looking at the odd degrees, positive. This is going to go from down to up. So this function is going to look kind of like that. Okay. So as x goes to negative infinity, this is the left side. So the left side is pointing down. So that would be a negative infinity. As x goes to infinity, this is the right side. We can see the right side of our graph right here is going up to positive infinity. All right, here we have a negative even function. Because the function is even, they're going to do the same thing. And because the leading coefficient is negative, they're both going to point down. It'll look like that. Actually, it's a quadratic, so it won't have this little dip in it. It'll look more like that. But you get the idea. Because they're both pointed down, the left and the right are going to go to negative infinity. All right. This one is sneaky. Okay. Some students hate these. They absolutely deplore these. Let me tell you why. is because you have to think and you can't just look at two numbers. So what you want to think about is if I multiply this all out, what is that first term going to look like? So let's think about this. If I multiply x to x to x, I'm going to get an x cubed in the front. There's no way for me to get any bigger than this, right? I don't magically have a fourth x laying around. So you don't have to worry about having like an x to the fourth in front. Count the number of x's. That is going to tell you your degree, that biggest exponent, okay? So because we have 3 x's, our biggest degree is going to be a 3. So we know this is an odd function. Now we have to figure out, is it positive or negative? So now we look at the leading coefficients of all the x's, and we multiply those signs together and figure out what the resulting sign is going to be. So we have positive x times positive x. A positive times a positive is positive. Times a positive x, that's still positive. But we have this negative in front. So once you multiply this all out, positive times positive times positive, you get a positive. Then you put this negative on the front. So we're going to have a negative x cubed in the front. That's all the information you need. You don't need to know what the x squared is back here. It's hard to tell, right? You'd have to do a lot of foiling, and we're not about that life. So we have all the information we need. We know that this is a negative odd function. So what that tells us is because it's odd, they're going to do opposite things. Because it's negative, the right side is going to go down. So it's going to look kind of like this. So opposites because of the odd, and then the right side goes down because the leading side is negative. So we're going to have right side is negative infinity, left side is infinity. Here, count the x's. 1, 2, 3, 4. So we're going to have x to the fourth, even, positive, 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 positive. We're going to have a positive x to the fourth. So both do the same thing. They're both going in the positive direction. And that's end behavior. All right. The other thing you're going to be responsible for knowing is how to find all of the key features of a given graph. So we're going to have to look at a graph and find some stuff. The zeros, the domain, the range, the maximum, the minimum, and then the AROC. This is the average. That's not how you spell average. Rate of change. There's a formula that I'll give you in a sec. Okay? So let's find all this information. The zeros, these are the same thing as x-intercepts. So we're just looking for where does it touch the x-axis. So it's right here, and right here. So we have -1. We have -1, 0. We have -1, 2, 3, 4, 5, 6, 7. -7, 0. Why does it look like that? Sorry. And then we have 1, 2, 3, 4, 0. Okay. So there's our 3 zeros, the 3 places it touches the x-axis. Now, let's talk about domain. The domain for every single polynomial in existence, every single polynomial, is all real numbers. That's actually the symbol for real numbers. Hold on, let me try that one more time. All real numbers. And then there's a symbol for this phrase. It's this. It's called double R. Anyway, it's important to know sometimes. Not important to know. I mean, yeah, important to know for sure. Okay. Now, range is a tricky part. Not all polynomials have the same range, unfortunately. So we have to look at this. We have a graph that's going up forever. We have an arrow pointed up. This means it will go up to y equals infinity. Okay. Then it comes down, 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 curves back up, drops back down. Then we have an arrow pointing down. This means it's going to go to y equals negative infinity. So our range goes down forever and it goes up forever. That's everything. So the range for this graph is also all real numbers. But we're going to see some that aren't all real numbers. Okay? We'll get there. All right, maximum. Keep in mind that these are called relative maximums. We're looking for hills, peaks, and then points where the graph drops down from. Okay? We have a hill, it's right here, and there's our max at 1, 2, 1, 2. So 2, 2 is our maximum. For our minimum, we're looking for valleys like U's, V's, and then this thingy flipped over. So a point where the graph goes up from it. We have a U, and the bottom of that U is right there at negative 1, 2, 3, 4, negative 1, 2, 3. So negative 4, negative 3. Okay. So those are, you're just reading off the graph. You find the ordered pair and you tell me the ordered pair for the min and the max. Okay. Our average rate of change, we need a formula. And you're going to love this formula. You actually know this formula. But if you don't, you should get a tattoo of this formula. That'd be so tight. Go ask your mom or dad. Say, Mom or Dad, is it cool if I get a tattoo? And then your parents will say, absolutely not. No child of mine is going to mark up their body with filthy tattoos, right? And then you're going to say, no, mom. This isn't some dumb butterfly on my lower back, right? This isn't like live, laugh, love on my forearm, or my last name on my forearm, or something lame like birds, right? This is something important, mother. This is a math formula that I'll need for the rest of my life. And then your mom will say, oh yeah, that sounds cool, go ahead. And then she'll sign off the little form and you can go get it. The formula is M is the rate of change. Slope is y2 minus y1 over x2 minus x1. So these are from the ordered pairs x1, y1, and x2, y2. Okay. You'll know you have these set up correctly because the 2's will be stacked and the ones will be stacked, meaning the ordered pair will be stacked on top of itself. If you have like a crisscross like that, you've done it wrong. Okay? So it doesn't matter really which point is 1 and which point is 2. Someday it might, but for you, not really. So just pick these two. We're looking at the min and the max. So just pick 1 to be 1 and 1 to be 2. So we'll say this one's 1, this one's 2. The real rule is the one farther on the right should be 2. But again, as long as you have them stacked, your number will come out correctly. So, all right. So our maximum, this one is 0.2. So we'll put those in first. We're going to have 2 over 2, put our minus signs from the equation. Then 1 is our minimum. So we're going to have y, negative 3, over the x, negative 4. And now we simplify this. So minus and negative, same thing as plus. 2 plus 3 is 5. Minus and negative, same thing as plus. 2 plus 4 is 6. So our average rate of change is 5 over 6. That means the slope, if I drew a straight line from these 2 points, the slope of that line is 5 over 6. And that's what the average rate of change means. All right, let's do, increasing, decreasing, and end behavior. You're going to love this. Then we're going to look at 2 more graphs real quick and just look at some other stuff. So increasing, decreasing, end behavior. This can be tricky. All right. Let's start with end behavior because this looks the easiest. Lucky for me, I still have it copied. Okay. So as x goes to negative infinity, remember this is the left side. So we look at the left. Is this pointing up or down? Up, Mr. Barton. Up means positive infinity. So f of x, the same thing as y, is going to positive infinity. On the right side, we look at the arrow. Is that going up or down? Down, Mr. Barton. So that means we're going to negative infinity. Done. All right. We got the easy part out of the way. Now we have to look at everyone's least favorite thing. Increasing, decreasing intervals. We've done these before and you loved them. So let's just remember how much we loved them the first time and then let's get them done. All right. So increasing, decreasing. Remember, we draw our little guy on there and he's got a disease. He can only walk right across the graph. So right now he's walking down. So that means we're starting with a decreasing. So he's decreasing, 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 decreasing until he gets right here. I would draw a vertical line. Okay. And then I would put a little down arrow there. So I know this is a decreasing section. Okay. Then he's going to walk up, starting here, going up, 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 till he gets right here on top of this hill. Draw a vertical line. This is an increasing section. Then, once he rounds the top of the hill, it's all downhill for the rest of his life. He's walking down forever. Okay. If you draw these vertical lines and you put these arrows, this will make this a lot easier. So, this section is decreasing. We need to know where does it start. You want to just think of these like walls. And you want to say, where's the left wall and where's the right wall? And we're looking at the x-axis. So the left wall, there is no left wall. It's way over here forever at negative infinity. So decreasing will start at negative infinity. And then where's the right wall? It's at negative 1, 2, 3, 4 on the x-axis. So he walks from left forever to left 4 from the origin. This whole section in here is decreasing. Okay, now we're increasing. Where's the left wall at? It's still at negative 4. We haven't moved it. So we start here at negative 4, and then we walk uphill to the right. How far right do we go? To positive 1, 2. Okay, that's the increasing section. Now decreasing section. Where's the left wall at? Right here, still at positive 2. We need to put a union to connect these. 2. And then how far is the right wall? There isn't one. It's over here forever at positive infinity. And that's our increasing, decreasing interval. All right. We have 2 more examples we need to do. They're going to ask you to graph some. And you're going to say, Mr. Barton, I don't know how to graph them. Luckily, you have this sweet tool called Desmos. Here, Desmos. This is the website you're going to go to. It should be part of your homework for my class anyway. If you're some like poor kid living in like Kansas watching this, Google Desmos. It'll help you graph. Hopefully you're not watching this 70 years in the future and Desmos is like no longer a website. In which case, you're going to have to do it the old-fashioned way and just count. By then, you'll probably have, like, talking dogs that can tell you the answer, right? Hopefully. So, you go to Desmos. You'll type in the equation you want to look at a graph of. It'll look just like this. You don't even have to put y equals. You can if you want, but you don't have to. You type it in, and then Desmos will mathematically give you a graph. Once you have the graph, all you have to do is take your little arrow and then you just click, 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 and it'll put those points on the graph with ordered pairs and tell them to you. So that'll give you most of the information that you need. So zeros. All right, here's a 0 right there at negative 0.8 0.666, 0. And you're going to say, Mr. Barton, you forgot the 0 in front of the decimal. It really doesn't matter. It does not matter. Some math teachers are really picky about that. I am not. I prefer not putting it. I typically don't. I think it's a waste of space. But, you know what I mean? I'm not going to tell you how to live your life. Here's another 0 at 0, 0. And here's our last 0 at 0.866, 0. All right. End behavior. We'll just use our copy paste tool here. Why is that like that? Okay. So on the left side, x goes to negative infinity. That's left. We're going down. So this will be negative infinity. X goes to infinity. That's the right side. We're going up. So that's infinity. Domain. Domain for every single polynomial is all real numbers. Range, we go down forever and we go up forever and we cover everything in the middle. So that's everything. Our range is also all real numbers. Okay. Let's look at one more. Oh, no. Okay. I'll make up one more for us because we haven't seen one where the range isn't all real. All right. Here's our function. We go to Desmos. We type it in. We get a pretty looking graph just like this. Okay. Zeros. Right there. Right there. Right there. You just click on the graph and it tells you. So we have negative 0.879, 0. We have 1.347, 0. And we have 2.532, 0. Maxima. We're just looking at that top right there. We're at 0, 3. Minima. We're looking at this little valley right here. We're at 2, -1. Average rate of change. Hopefully, you've got that appointment for that tattoo made. M equals y2 minus y1 over x2 minus x1. Pick which point you want to be 1 and which point you want to be 2. I'm going to say this one is 1. This one is 2. So here's point 1. Here's point 2. I'm going to fill in my stuff. 2, I'm going to take my y and my x. Y goes on top. X goes on the bottom. Minus signs from the equation. Then we fill in point 1. Y goes on top. X goes on the bottom. And simplify. -1 minus 3 is -4. 2 minus 0 is 2. And we can reduce this one. This is -2. And there's our answer. All right. That's the end of the notes, but we need to look at something really quick. Actually, let me do it on here. Let's pretend we need to talk about domain and range. This one's actually better. Okay. Let's pretend that our graph does this instead. And then this doesn't exist anymore. Okay. Here's our graph. It's just this purple part. Let me actually even cover it up so that we don't have to even like waste brain power looking at this. There you go. That's your graph. Okay. So let's look at this graph. We want our domain. Domain for every single polynomial in the whole world is all real numbers. Okay. Range, though, is no longer all real numbers. We don't go down forever and up forever. So we have to look. We have an arrow pointing down. That goes to -infinity. That's what the arrow means. It goes forever and down is negative. So our range will go down to -infinity, but it doesn't go up forever. It goes up, 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 reaches a maximum, and then turns around and comes back down. This number right here is going to be your maximum y value. What's the highest on the y-axis you ever get? Well, let's look. This is lined up with 1. So our range goes from -infinity to 1, And this should not be a parenthesis. It's touching, right? There's a point there. It should be a bracket to show that it's included. Okay, so there's your notes. If you need more help with that, please go to the WebEx and please say, Mr. Barton, I can't figure it out. You're too mean. You give me way too much homework. I'm going to fail and my mom's going to get mad and then she's going to tell me I'm never going to be anything when I grow up and she doesn't want me to live with her for the rest of her life and she doesn't even really like me and she said she won't buy me any more Pokemon cards and she won't give me the Drip Goku jacket and you're ruining my life. Tell me. Let me know. Dang, don't bottle that up, kid. Oh my gosh, you're going to hurt yourself. If you need help, ask for help. Okay? I'm sure your parents love you. I'm sure your mom will get you that drip jacket, but you got to pass math. So if you need help passing math, go ask for help. Until next time, have a wonderful, until next time I see you. Adios.